let's go to the proof. How do we show that the angle at the center of a circle is twice the angle at the circumference? First of all, let's write the theorem. The angle that an arc of a circle subtends at the center is twice that which it subtends, is twice that which it subtends at any point on the remaining part of the circumference. Now that's a theorem. That means this is a circle, for example. If this is the center of a circle, this is a radius, and this is also a radius. If this is an arc, see the arc is facing up, so the angle it subtends at the center is this, because you see that it also faces up, and this arc subtends this angle at the circumference. This is the arc. It subtends this angle at the center and this angle at the circumference. The theorem states that this angle which is subtends at the center, is twice this angle which is subtends at the circumference. That means if this one is 40 degrees, this will be 80 degrees. If this is theta, if the angle at the circumference is theta, the angle at the center is theta. So, and you know too that if this is theta, that means this will be half theta over 2. Now, so let's see the proof. Now, what are we given? We are given a circle APB with center O. Given a circle APB with center O. What do we want to prove? What we want to prove is that angle AOB is equal to 2 times angle APB. Now, construction. This is what we are going to do to prove that. Join P to O, point P to O, and producing it means extend it to, and produce it to any point Q. And what's the proof itself? This is the proof. Let's have a diagram. This is a circle. This is center of a circle. This is a radius. This is another radius. Let O be the center of the circle. Now, let's have this. That's an angle at the circumference. This is point A, point P, and point B. So, construction is join P to O, join point P to point O, and produce it to any point Q. any point Q. Now, let this angle be x1 and this angle be x2. This angle be x2. Let this angle be y1. Let this angle be y1 and this angle be y2. y2. Now, how do we do the proof? We know that length OA is equal to length OP. OA is equal to OP, and the reason for that is that they are both radii. Singular is radius and plural is radii. OA is equal to OP. The reason for that is that they are both radii. OA is a radius and OP is also a radius. Now, what that simply means is that angle x1 is equal to angle x2. And the reason is that the base angles of an isosceles triangle are equal. If OA is equal to OP, that means triangle OAP is an isosceles triangle, which means its base angles are going to be equal. So that's why angle x1 is equal to angle x2. Now, that means x1 is equal to, therefore, x1 equals x2. The reason is base angles of isosceles triangle OAP. Now, we also know that angle AOQ, which is this angle AOQ, this angle, is equal to angle AOQ, which is this angle, is equal to x1 plus x2. And the reason for that is that the exterior angle of a triangle is equal to the sum of opposite interior angles. This is a triangle. If I extend this length, there's going to be an exterior angle here. This is an exterior angle to this triangle. And you know that the exterior angle of a triangle is equal to the sum of opposite interior angles. This x1 and x2 are the opposite interior angles. So that means this angle AOQ is equal to x1 plus x2. And the reason is exterior angle of a triangle is equal to the sum of opposite interior angles. So that means AOQ equals x1 plus x2. The reason is exterior angle of triangle OAP. Now, we know that x1 is equal to x2. So instead of writing x1, I can write x2. And instead of writing x2, I can write x1 because they mean the same thing. So I'm writing x2 instead of x1. That simply means x2 plus x2, which therefore means angle AOQ is equal to 2x2. So here I'm going to write, it is x1 plus x2 because x1 is the same as x2. So I can write x1 wherever I'm supposed to write x2, and I can write x2 wherever I'm supposed to write x1. Now, so similarly, angle BOQ, I know that similarly OB is equal to OP. They are both radii. OB is a radius, OP is also a radius, and they are equal. OB is equal to OP. And the reason for that is that they are both radii. Now, that therefore means angle y1 is equal to angle y2. y1 is equal to y2. Base angles of isosceles triangle. Base angles of isosceles triangle OBP. This is the isosceles triangle of isosceles triangle OBP. OBP. Now, the exterior angle QOB, which is this angle, is equal to the sum of opposite interior angles. And that means QOB is equal to y1 plus y2. y1 plus y2. QOB, angle QOB is equal to y1 plus y2. Exterior angle of triangle OBP. Exterior angle of triangle OBP. Of triangle OBP. Of triangle OBP. And now I know that y1 is equal to y2. So instead of writing y1, I want to write y2. So this is same as y2 plus y2, because y1 is equal to y2, and that therefore means angle QOB is equal to 2y2. So, and we can see that angle AOQ plus angle QOB, angle AOQ plus angle QOB is equal to angle AOB, which is the whole of this. This angle plus this angle is equal to the whole of this. So, angle AOB is equal to angle AOQ. Let's check that again. Angle AOB is equal to angle AOQ plus angle QOB. It's equal to angle AOQ plus angle QOB. And that's equal to angle AOQ is 2x2. That's 2x2. That's 2x2 plus angle QOB, which is 2y2. 2x2 plus 2y2. And that simply means 2 into bracket x2 plus y2. That's the same as 2 into bracket x2 plus y2. And we can see from the diagram, you can see that x2 plus y2, which is the whole of this angle, is angle APB. x2 plus y2 is angle APB, and that's equal to 2 times angle APB. And that's the proof. Therefore, angle AOB is equal to 2 times angle APB. Angle AOB is equal to 2 times angle APB. And that simply means the angle at the center of the circle is twice the angle at the circumference. So that's a proof very, very simply. That's a proof very, very simply.